Welcome to week 4 of the Network Softwarization Principles and Foundations class. We're still in the second module on software-defined optical wide area networks and radio access. And in this week, we'll be talking about how we can enhance software-defined networks by making the optical physical layer more programmable. This is an outline of what I'll be talking to you about today. We're going to start with a review of wavelength division multiplexing in optical networks. We'll go back and see how they were first adopted and the technological changes that enabled their growth into where we are today with optical reconfigurable networks. The second topic will be to look at what is known in the communications theory as the Shannon limit. So this gives you the limit of how much information you can put through a channel, in this case the fiber channel. Because when we understand how technology is meeting these limits, we will be able to identify some new opportunities or how these developments could be used to make gains on the network layer once the physical layer has been optimized. That will bring us into the third topic today, which is on elastic optical networks. So this is seen as the next generation, if you will, of reconfigurable optical networks and the basis for the next generation of software-defined networks. So once we understand how the architecture is being envisioned for this next generation optical network, we can look into how the physical layer constraints play into the kinds of optimizations we can seek in the elastical optical network. That brings us to the fourth and final topic, which is about the physical layer and how we are achieving the goals of making it more programmable. In particular, we'll look at two very popular solutions under examination, known as the Nyquist wavelength division multiplexing approach, or the optical orthogonal frequency division multiplexing approach. And again, we'll be focusing on the constraints on performance for each of these solutions and how they might make for better choices in elastic optical networks. Finally, I'll give you some concluding remarks if we finished our overview. So optical fiber. Why do we use optical fiber? Why has the growth in communications of optical fiber been so significant? In fact, we could say that today most systems either have optical fiber or are wireless. And we've really gotten pushed out most of the wired communications such as twisted pair and coaxial cable. They still exist, of course, but the future is clearly on the optical side. So the advantages of optical fiber are, first of all, tremendously low loss. We're talking about 0.4 dB per kilometer of loss. And in addition to that, a tremendous passband, an amazing amount of available bandwidth in the optical fiber, something on the order of terahertz. And in addition to that, despite having all these great qualities of being low loss, wideband, it's also very low cost. Tremendous advantages. If I want to compare it to coaxial cable, the loss is in the tens of dB per 100 feet. So the loss, there's really no comparison. And the passband, typically we're talking about a few hundred megahertz for that coaxial cable if I want to keep cost cheap. And if I want to get wider bandwidth, the cost goes up tremendously. So optical fiber, hands down, the choice used to be just for long distance, but even for medium distance, even on the 20-kilometer or in the data center, all of these applications now find the advantage of going with optical fiber. So short distance like data center, access networks on the 20-kilometer scale, or transoceanic covering the globe, we're all looking at optical fiber in these applications. Now let's look at communications techniques that were used in optical fiber. The first technique used was called on-off keying. And of course the greatest motivation for that was that it was cheap. It would be able to communicate in optics as fast as the driving electronics could be driven. And on-off keying is very simple. For a logical 0, we send no light. For a logical 1, we send a certain level of power on the optical light. So it was very easy to achieve very fast components and very inexpensive. And because the electronics bandwidth was not tremendous, the terahertz bandwidth available in the optical fiber seemed limitless. So with such a tremendous available bandwidth, every time we had to increase capacity, we simply added a new transceiver. So if we think of this as the fiber with terahertz bandwidth, we have one transmitter and receiver on a given wavelength. I could add another wavelength. There's lots of space, the fiber can handle a lot, and so the cost was just the cost of adding another transceiver. Well, that's good for short links, but it's not necessarily the case when I get to longer links. The loss is low at 0.4 dB per kilometer, but if we go to transoceanic links, when we are talking about thousands and thousands of kilometers, of course the repeaters are required. And so we would have to have a link that would create a new transceiver for each one of these wavelengths that were exploited as we made longer and longer links. So that meant that we had a lot of capacity in the fiber and we could exploit it. However, the cost per bit was pretty much fixed and that we weren't able to get many economies of scale. Every time I wanted to add more data, I had to create a whole new system. Only the cost of the fiber wasn't repeated, but remember, the fiber is low cost. It's the transceivers that are expensive in the end. So that was what I would call the first generation of optical communications. Then there was the development of a device known as the Erbium doped fiber amplifier, or EDFA. And EDFAs were real game changers in communications. Before the EDFA, we had this electrical regeneration of signals. You would actually, every partial link after the fiber, you would convert from optical to electronics, get your electronic bits, and then regenerate them in light for the next transmission. However, when we went to post-EDFAs, we used an amplification in the optical domain, which meant we did not have to convert the signals from the optical domain into the electrical domain. And on top of that, the EDFA would have one device, one amplifier, which would amplify all of the wavelengths that were present in the fiber. So it was a way to take long links and make them really, really cost effective. So instead of having a transceiver pair for each wavelength, I had one EDFA that would amplify all of the channels. What this meant is that the marginal cost of having a wavelength became very low, and the cost per bit started going way down. And this was the second generation, if we will, of optical communications. So one way that we could look at this evolution along the years is to look at what's been published as the experimental demonstrations as new technologies evolve. So we started out with the single channel in the green line. Let me go back there. A single channel on this green line was the progress that we made when we were using a single wavelength. And you can see that from 86 to 2006, you can see a steady growth somewhere in the range from 10 gigabits to 100 gigabits per second on a single optical fiber using a variety of wavelengths. Now we look at, using a single wavelength. Now we look at the multiple wavelengths, and we can see that the slope of the change, the slope of the increase changed tremendously. And that is because we could now, didn't have to use the electronic repeaters, and deployment of multiple wavelengths really, really took off. And we can see that that allowed us to go into the terabits per second communications on a single optical fiber. So we've seen that we can exploit multiple wavelengths in order to increase performance. And the question might be, how many wavelengths could we use? And to answer that question, we should look at the characteristics of the optical fiber. So here is the curve of optical fiber loss versus wavelength. So we have wavelengths in nanometers here on the x-axis, and here's the fiber loss coefficient in dB per kilometers. I mentioned to you earlier a number of about 0.4 dB per kilometer. Of course, with increases in the efficiency and the manufacturing of optical fiber, the loss has gone down over the years. And this is very modern fibers. And there's two kinds of fibers we'll see here. There's the typical single mode fiber, which has an absorption at 1400 nanometers band, which causes high loss at that wavelength. But new fibers, all wave fibers, have come a long way to make it actually pretty a smooth plot of fiber loss versus wavelength. But of course we can see in this graph that there are clearly some wavelengths which are much lower loss and other ones where the loss is higher. For instance, we might see in the 1300 nanometers band a somewhat acceptable loss in this range in the modern fibers, and we'll see those in shorter distance communications would be exploiting these bands. But for the long distance communications, we're more likely to see that in the what we call the C and the L bands, which are around the 1550 nanometer wavelengths. And it's especially in these bands that we see long distance communications because this is where the EDFA is most effective. So most communication systems are in the C and L band, although there are some on other bands which tend to be shorter distance, lower cost. However, we see that there's been a lot of economies of scale from all of the development efforts being made in the 1500s bands. So it's also quite popular even for shorter length, shorter distance links. So we've seen that wavelength division multiplexing really blossomed because we were able to exploit multiple bands, wide bands, and with cost-effective optical amplification. And in fact, we see here how many channels that we have seen exploited on these bands. And this is a fairly recent demonstration from September of 2017, where they use not an EDFA, not an erbium dope fiber amplifier, but actually one which is semiconductor based, so even less expensive. And we were able to get 86 channels in the C band and 92 channels in the L band. We can see that there are some sort of gaps in between the band which probably less well amplified and other reasons. But the total transmission over this fiber link was in the terabits per second. So we've seen that the wavelength division multiplexing has let us grow the capacity of optical communications tremendously from the gigabits per second in the early years to the terabits per second today. So when we get to these numbers of how many channels we can put into the waveband, I showed you the bands we could use, but there's a question about how closely we can pack these wavelength channels. And there's a trade-off because of course the tighter we pack them, the more information we can transmit. But we also are creating interference or crosstalk from the neighboring wavelengths. So what we see here in the bottom is sort of the additive white Gaussian noise, which should be the impairment that causes most of the errors. And what we'll do is we'll start bringing the wavelengths closer together until we get to the point that the errors are coming not from the unavoidable additive white Gaussian noise, but instead from the crosstalk from neighbors. And so this is how we fill up that capacity as much as we can. So we have wavelength division multiplexing, And we use these in optical networks. And what we'll see going on here is a description with different colors representing different wavelengths. And information could be routed from one transmitter to another receiver pair using the wavelength to choose the route along the network. And we can see these units, these switching units, which can read the headers and route the wavelength accordingly. So what I'd like to talk about next are some of those switching units we saw inside of the optical network and what they're required to do. We call these an optical add-drop multiplexer. So in order to do switching, that box that we saw in our network, this box, at the very least, it's got to be able to add a wavelength if we need to add one at that point, at that ingress point, or it's got to be able to drop it if we're at an egress point. Ideally, it would be nice if we could convert from one wavelength to another, but of course we can do routing without it. It's just we'd have richer routing opportunities if we could do wavelength conversion. It would also be able to scale as the needs grow for different kinds of cross connects. That means that we would like to have a higher degree add-drop multiplexer. So OADM, or optical add-drop multiplexers, were the major enablers for taking this wavelength division multiplexing and not only using it to increase the capacity of the fiber, but also use it as an element that could be used in routing within the network. Now, ROADM is the most modern version of this add-drop multiplexer, which is known as a reconfigurable optical add-drop multiplexer. And this was the first level of a software-defined network in the optical domain. So where you could keep signals in a purely optical state, just read the headers, convert those to electronics, or have some optically controlled headers too. But in any case, this was a key component. So when we look at these elements in a reconfigurable optical network, they would be called ROADMs. So these devices allowed us to reconfigure the routes as they went through. But with this optically routed network, we had the assumption that each wavelength was on a fixed grid. We laid out what wavelengths were available, and we policed them and let signals only go out on those wavelengths. Each of the data signals on each one of those wavelengths was at a fixed bit rate and could not be changed. So there's a very strict understanding about the communications at each one of these wavelengths. And this means that if we want to look at our resource allocation, which wavelength was available, what bit rate was available, it was a very coarse ability to route in the optical domain provided by these devices. It required a lot of grooming in the electronic domain so that we could do load balancing, so we could fill up the channel, so that we could allow the wavelength routing to occur. And when we have this coarse allocation of resources, that leads to a lot of over-provisioning and underutilization. That means I have to build a link for the peak traffic, and I will have spent more and have a higher quality link than maybe I'm going to be able to use at all time, hence the underutilization. I want to mention that I talked earlier about how tightly we could pack the wavelengths, and in the optically routed networks, that was one of the major reasons that we had to have these guard bands or a sufficient spacing between the wavelengths, because the routing ROADMs had a certain sharpness to the filtering, and because it wasn't ideally sharp, when we accumulated filtering across many hops in the network, the sharpness of the filter, the width of the filtered effective width would get smaller and smaller and cut into our channels. So there's another reason why we needed guard bands, not just to eliminate crosstalk, but also to maintain signal integrity despite going through many filters in the optically routed network. And this is a little diagram where I try to explain what I meant by that. Larger guard bands meant that this is the filter response of a ROADM at a hop. And so it goes through the first filtering device, and you can see we're going to be cutting off the corners of our data signal. And when we go to the next hop, we're going to filter it a little more, the next one more, and we will slowly degrade the quality of our signal. So if we leave lots of guard band, lots of space in here in between the channels, then this effective filtering, we can make our filters wider, and this effect will be less detrimental. So that is our introduction to wavelength multiplexing in optical networks. And now I'd like to shift gears and talk about how we are pushing, why did I end up saying terabits? How do we get from 86 plus 92, I forget the exact numbers, how do we get from these many channels until the final total throughput that we achieved? And that's related to what we call the Shannon limit. So let's start with the definition of the Shannon limit. So the Shannon limit says that when we have a channel which is ultimately limited just by the amount of additive white Gaussian noise that we're adding to it. In this case, the maximum capacity of the channel, and we mean by capacity the number of bits per second that could be sent through that channel, are related to two quantities, the signal-to-noise ratio and the bandwidth. And as you can see, this is a very simple expression, that this capacity is equal to the bandwidth times the log base 2 of the sum of 1 plus the signal-to-noise ratio. So we can do a manipulation of this equation to make it a little bit more meaningful, and I'll tell you why. Because in an additive white Gaussian noise channel, that's a channel where there is a given fixed power spectral density for the noise. It's constant across all frequencies. So as I change the wavelength, as I change the bandwidth, W, the bandwidth of a signal, the noise that's present in the passband of the signal is related to the bandwidth. The larger the bandwidth, the more noise I have. If I increase the bandwidth, I'm adding more noise. So that means that the bandwidth and the signal-to-noise ratio, because the denominator of the signal-to-noise ratio is the noise, they're somewhat related to one another. And so that's an equation that's simple, but it's hard to really get a grasp on. So what we do is we can put it in an alternate form, and we can do some manipulations to put it in the equation in this form that you see. And this form just manipulates the definition of the signal-to-noise ratio to come up with instead something based on the energy per bit. And in fact, energy per bit is the quantity that we use to determine the performance of a digital communications system. And we can see that now the capacity, when it occurs, is always in the ratio of capacity divided by available bandwidth, W. And so that's important because the capacity per available bandwidth is what we call the spectral efficiency, because it tells us how much information are we getting through, given that we have a certain slice of bandwidth available. So this is a very useful way to render Shannon's limit, or the equation for the Shannon limit. So let's look at a graph of this Shannon capacity. So we can see here on the x-axis we have the energy per bit, and this is a kind of signal-to-noise ratio. We call it the energy per bit, and this is in dB. And then here we have the spectral efficiency. And so we put the line here where we see that for spectral efficiency that's above 1, we're getting more and more information out in a limited bandwidth. But here at the bottom, instead, we're using a lot of bandwidth in order to make our communications more reliable. So what the limit says, this is the equation that we just saw. So we have the spectral efficiency, this is the C over W, and this is the energy per bit, and everything underneath this curve is what we call achievable. This is the limit. We can't expect to do anything more than that. That's actually the most information we can push through the channel. So everything below is achievable. And what's also interesting is we can look at the asymptote here. So as we go along this curve, going to the right here, where this is going where efficiency is getting better. Spectral efficiency is going higher. Here we have spectral efficiency going to 0 in this direction. And if we think of this, we can think of this as we trade off spectrum in order to be able to get good communications, despite the fact that we have very, very little energy per bit. In fact, here at -1, we can see that there's more noise than signal present. And there's actually a limit about how much we can trade off that spectrum in order to, so how weak can my signal be and still be able to achieve transmission. So this is what we mean by the Shannon limit. But Shannon was famous for having given us this limit, but not told us how we could achieve this limit. So I'm down here somewhere, and I know I can do better. I want to push up and get more spectral efficiency. That means if I have a given amount of bandwidth, I have the C band and the L band, and I want to get more bits per second out of that amount of bandwidth. I want to push it and get closer to the limit. He didn't tell us how to get there. He just told us what the limit was. So how do we get it? In the end, we've developed what we call forward error correction, which is digital signal processing that allows us to add redundancy to data in a structured way so that at the receiver we can actually use the redundancy that we've added to correct errors as they occur. And I tell people that for me it's almost like magic. I can look at a signal which is so corrupted by noise that it seems impossible to be able to decode it, and actually running some DSP we can have the signal pop out with some very good reliability. The second way we can try and achieve get closer to the Shannon capacity is by using what we call advanced modulation, which lets us do some of this exchange of bandwidth for capacity, or to achieve more higher ratio of capacity to bandwidth. So I'll be talking to you about how we're able to do that. First, just a few words on error correction codes. So as I mentioned, we add redundancy to bits at the transmitter, and then we use sophisticated DSP at the receiver to exploit that redundancy in order to correct errors. Typically when we talked about error-free, what we mean by error-free is that there are very few errors, so that the bit error rate is something like 10 to the minus 12 or 10 to the minus 15. That means I'll send 10 to the 12 bits, and on average only one of those bits will be an error. So for these targets, what I can do is I can use forward error correction in order to achieve them, and that all I actually have to achieve is something like 3 times 10 to the minus 3 or 1 times 10 to the minus 2. If I'm able to just get the bare channel to where it only makes 1 error in 100, that's enough for me to use my DSP to actually drag it back down to only 1 error in 10 to the minus 12 or 1 error in 10 to the minus 15. So that shows you the power of these error correcting codes. I mentioned 2 levels here. These are known as thresholds. So if my bare channel with no correction can reach these levels, then when I add forward error correction, I'm going to be able to hit these what we call error-free targets. But of course there's a cost. I don't get this for nothing, and what I have to do is I have to trade off some of my capacity. So I have to introduce an overhead. I say I add redundancy. So how much redundancy do I add? Well, if I add as little as 7% redundancy, so for every 100 bits I send, 7 of those bits are actually forward error correction bits, that's enough for me to be able to take 3 times 10 to the root 3 down to 10 to the minus 12 or 10 to the minus 15. And so we can think of the redundancy reducing our spectral efficiency because I'm using the same bandwidth, but instead of sending 100 bits, I'm only sending 93 bits. Now, if I want to be able to use a channel that's much noisier, then I have to put more overhead. And so you see that I can trade off, giving up some of the spectral efficiency up to 20%, but I can send information in a channel that's much noisier. So that's how forward error correction is being used to help us meet the Shannon limit. But that's not enough. So I like to talk about squeezing the Shannon limit. How is it that we got there? Well, in terms of the optical fiber, the first thing we did was we used fast electronics. So if we look here on this axis, this is the symbol rate, how fast we're pushing through data. And so with the years, as electronics has gotten faster, we're pushing up the data rate that we send. Then we used multiple wavelengths. So as we use more and more wavelengths, we're piling up in the frequency domain how many wavelengths we're able to exploit. So as the symbol rate goes up, each one of these channels gets fatter because I'm able to put more data on it, and then I sort of line them up. Then if we want to go farther and try to reach Shannon's limit, we have to introduce what's called advanced modulation. And that's shown as another axis here on where we're trying to go to push our performance. And what we mean by advanced modulation is that we will modulate both the phase and the amplitude of the light. Now, modulating both phase and amplitude is something that has been going on for a long time in wireless and in other electronic wired communications. It was not used in optics, not because we couldn't, but because we had it so good already. We had so many wavelengths we could exploit. Our on-off keying was so inexpensive that we used on-off keying for years and years, which was very simple again. It was just there's power or there's no power. Now instead, with advanced modulations, I'm going to play with the electric field of the signal being transmitted and manipulate both the phase and amplitude in order to imprint the data that's going to be communicated in these two things. And this way, instead of having just a binary level to only be able to send a 0 or a 1 in a given interval of time, I can send out much more information by exploiting the phase and the amplitude. So that meant that we need new transceivers in the optical domain that were capable of modulating the phase and, of course, adjusting the amplitude, but that's done more easily. And we had to have receivers that were able to detect the phase. Now, since photodetectors, which were commonly used in on-off keying, only detected the power of the signal, we had to go to a new type of transceiver that used coherent detection. So in order to really push the Shannon limit, we had to go to this, what we call advanced modulations. So advanced modulations can take many formats, and we have a graph here on the right of several different constellations. And constellations are how we are manipulating the phase and the amplitude. Here's on-off keying. In the center, I'm not sending any energy. And then on this other dot, that's when I'm sending energy, and I don't care what the phase of the signal is. So this is a plot of what we call the in phase and the quadrature. The x-axis is, if you will, the projection on a cosine, and the y-axis is a projection on the sine, and the angle between them gives you the phase of my electric field. So this circle means that, and the on-off keying, I didn't care what the phase was. It could be anything. I would just detect the power. But as we go to advanced modulation formats, for example, QPSK, I'm going to actually have 4 different phases that I'm going to use. And depending on which phase I receive, I can now have 2 bits of information conveyed. So a constellation with 4 log 2 of 4 is 2, so I can have this symbol be 0, 0, this one be 0, 1, this symbol be 1, 0, and this symbol could represent 1, 1. And so I can send more information in the same amount of time. So here at a given time interval I would send 1 bit, here I could send 2 bit. And we can generalize this idea. Here it was just the phase that was changing, but if I change both phase and amplitude, I can create a two-dimensional geometry of any kind and use that as my strategy for sending more information in the same time slot, and of course in the same time interval. So that means that on a single wavelength, one wavelength slot, in the same amount of bandwidth, so I have my my wavelength grid defined, within one of those slots, I can now send more bits in that same slot. So I get much higher spectral efficiency. And then I'm pushing myself higher, closer to that Shannon limit, because I'm driving up my spectral efficiency. And of course, if I go to multiple wavelengths, I can do that within each wavelength slot. So I can have different modulation formats, whether it's QPSK, 8 QAM, 16 QAM. QAM refers to quadrature amplitude modulation. It means I'm modulating both the phase and the amplitude. And what we can start to see is that, of course, we can get more bits per slot, and we're pushing up the capacity. And that's on a per wavelength basis. I said in order to achieve this move towards Shannon limit, we had to introduce new devices. So this is the optical coherent detector that is needed in order to be able to detect the phase. So this is a photodetector. And I used on-off keying. The only thing I needed was a photodetector. I didn't need anything else, just one photodetector. Now, in order to be able to detect both phase and amplitude, now I need a bank of 2 photodiodes. I have to rotate 90 degrees in order to get the in-phase and quadrature. I also have to use a local source in order to beat against it so that I can go from a square law device measuring power to a signal which is proportional to the electronic field as opposed to the field squared. And of course this led to much more costly components and also much more digital signal processing. But at a certain point, the economics made it worth going to this greater complexity in order to get great increases in capacity and to start approaching the Shannon limit. And today, integration techniques are driving down the cost. And in fact, the QPSK solution with 4 points in the constellation is common in commercial deployments, and higher modulations are coming. Now, when I made this shift to working in phase and amplitude modulation, it also allowed me to do something called polarization multiplexing. So it was kind of a bonus. So we can see as we move into more sophisticated systems, there are more capabilities that are coming online that we can exploit. And that is why we have 2 different sections in this receiver. One section is dedicated to detecting one polarization, and the other section to the second polarization. And this doubles the capacity of what can be transmitted. So on a given wavelength, I'll send communications on an X, let's call it an X polarization. I can send another one in a Y polarization. These 2 are orthogonal. And if I use enough DSP, I can separate the communications even though they're carried on the same wavelength. In terms of constellation generation, we also had to go to more complex modulators. As you can imagine, the on-off keying modulators were quite easy. Send power, don't send power. Now I have to be able to manipulate both the amplitude and the phase, so that required new, what we call IQ modulators. And it also required laser sources, which were of higher performance. The noises in phases of the laser source would make it very difficult to detect differences in phase. And so we need laser sources with what we call a very small line width, or on whom the native phase is fairly stable. So we've seen how we can get to the Shannon capacity, and that is by using these constellations, higher order QAM, higher order modulations. So a low M, I'm at this section of the curve, and as I make M larger, the number of points in this constellation, I add more points, I'm getting up higher and I'm moving higher on the spectral efficiency. I'm getting closer to the Shannon capacity. And we also talked about using forward error correction, and the forward error correction just makes us take that movement along the low M to higher M. We're just pushing it closer and closer to the actual curve by using forward error correction. So if I have a fixed bandwidth, like I'm on the C and L band, which means my W is fixed, if I want to push through higher capacity, what that means is I have to become more spectrally efficient. So I have to drive up higher on this curve. And of course I'm limited somewhat by energy per bit, but if I have a lot of energy per bit, then I can push up here into modulation formats which send more bits per symbol to increase capacity. And that brings us to the what we call the second wave of the capacity increases. So we had the on-off keying in the early years of optical communications. Then we saw the WDM, and so what I'm plotting here is the year versus the capacity, how many bits per second we were able to push through the fiber. So we started with on-off keying, then we saw WDM come into play, and we saw the increase in the carrying capacity of the fiber, and finally we go into the high spectral efficiency coding, and we can see the increases now are coming from that. So I want to finish this section talking about technology readiness. Why did I take you through how we push to meet the Shannon limit? Because the efforts to meet the Shannon limit produced a much richer solution set for what we can do to manipulate our signals. So we now have coherent detection, and we're driving down the cost of coherent detection by having receivers and modulators whose cost is coming down. We've developed strong DSP. We're exploiting the low cost points of VLSI in order to achieve very good performance. I mentioned FEC, but there's other DSP that we're using to keep our signals very high integrity. So these coherent detection, strong DSP, all in integrated components. We're looking at silicon photonics so that the devices could, for optics, could actually be integrated with the manipulations in electronics. All of these are pushing down costs and creating a rich set of devices that we can exploit. And this is what has enabled us to move to more flexible optical networks. So here is the overall view of the hardware. I've showed you before the transmitter and the detector, and here is all of the signal processing that I mentioned. And I suppose I should have mentioned the digital to analog converters and the analog to digital converters, which are also important enablers of coherent detection and advanced modulation. Which brings us to the next topic, which is the elastic optical networks and how new paradigms for routing in optical networks can be created using these technologies derived from the Shannon limit. So where are we today? We started with traditional WDM, and we had fixed bit rates. We had 10 gigabits per second, 40 gigabits per second, and 100 gigabits per second is coming out now. Standardization is underway for 400 gigabits per second, but they're fixed bit rates. We also have fixed channel spacing. And using dense WDM, we have either 50 gigahertz spacing or 100 gigahertz spacing, depending on the system we're looking at. We have reconfigurable optical networks today using ROADMs with limited degrees in these ROADMs. And we're working on this traditional WDM structure with a fixed grid, fixed bit rates, a couple bit rates to choose from, but they're fixed. And we use what are called wavelength routing and wavelength assignment algorithms in order to route within this reconfigurable optical network. But we've been looking to push the physical layer, and now we want to look to how we can push the network layer to try and get the most out of all of these advances that we've seen on the PHY level. So flexibility is the key to the advances we're going to make. We're going to scrap the fixed grid WDM approach, and we're going to go to something that's more elastic. So there are different vocabulary that's used in the literature. One of the most common is calling this an elastic optical network. So flexibility, we're going to call it an elastic network, or sometimes we call it a flexible network. And sometimes we call it Flexgrid, because instead of a grid, we're using flexible version. Sometimes we call it gridless or just tunable. But they all come down to the same thing. Instead of having a fixed allotment, wavelengths always come on fixed positions. We're going to be able to say that in one link, the wavelength may be at one position, on another link it may be another position, and also the amount of information carried on that wavelength could vary from one part of the network to another part of the network. So we typically tend to use frequency rather than wavelength, and to distinguish a little bit to these two different concepts. But the slots, the important thing is that they're variable in size and they're variable in placement. They're not always at the same place. So what is it we're trying to overcome in what deficit are we trying to overcome as we go from the old reconfigurable optical networks to the new elastic networks? Well, it's this concept of having over-provisioned the network in order to meet peak traffic and the underutilization of resources. So it's really this idea is where we're playing in order to see the increases in overall performance. So let's take an example to see how these advances could be achieved. Suppose that we have fixed 50 gigahertz channels, and each one of them able to achieve 100 gigabits per second. So this is really one of the more advanced systems that are being deployed today. So we have a simple mesh node with six nodes, and we have some information that we're trying to push through, and this one has three requirements. We want to go from A to C is the first link, and we want to send 200 gigabits per second on that link. So in this case, we'll have two WDM slots which are going to be used. So from point A to point C, we're going to reserve two wavelengths and send information on this connection number 1 in that way. Now we see the second requirement is from F to C, and so we're going to have to send 40 gigabits per second. Of course, there's only a fixed bit rate, so even though I only need 40 gigabits per second, I'm going to use a 100 gigabits link. So now here we have the underutilization. So I'm going to add another wavelength, and it's got to be used from F to A and then all the way from A to C. And then finally, in the third one, I need to send 40 gigabits per second from link B to C, so I add another wavelength, and again I have to provision with 100 gigabits per second, even though I only need 40. So what do we do when we go to a flexible solution? So how would we meet the same requirement? For that, I would send one fat frequency allocation from A to C. So I have here we have a double wide slot for the link from A to C. Now when it comes time for F to C, I'll take a second wavelength, but I only need 40 gigabits per second, so I'm going to use a half width slot instead of a double width slot. So I'm using less of the spectrum, sending the information. And now for this B to C, I need to send another one, and in this case I also have to send 40 gigabits per second, but I'm actually going to use a quarter width slot for the link from B to C. And you may ask, why a quarter width for B to C and a half width for F to C, even though they both are looking at 40 gigabits per second? And the reason is because the distances are different. When I have to go from F all the way to C, my signal is going to have to travel a longer distance than the signal from B to C. Longer distance means greater attenuation, signal is weaker, less signal to noise ratio. which means that I cannot use the most advanced modulation formats. But on the shorter link, my signal-to-noise ratio is very good, and I can try and squeeze in more bits per symbol. So I'm actually able to have higher spectral efficiency because it's a shorter link. So we can compare these two to identify the spectrum savings. And so we can see that because I'm sending information in variable width slots, I'm able to have significant savings in the spectrum. I also have transponder savings. Transponder savings means that because I could have one transceiver that could handle the 200 gigabits per second, I didn't have to have two units, each sending 100 gigabits per second. So the programmability of my transceiver helps me get spectrum savings, and it's also going to give me some cost savings because I can reduce the number of elements that I need. I said that we're going to use frequency slots, and so the standard that we're moving forwards for elastic optical networks is envisioning 6.25 gigahertz steps, so that we start with the base of the WDM grid, and then we just say we're going to add very, very fine slots, and this is the finest spectral granularity that we have in the system until we get to the position that we would be transmitting on. So fixed filter widths are no longer appropriate because I need to have filters of different widths depending on what how I'm trying to exploit the available spectrum. So ROADMs were, the R is for reconfigurable. So they were reconfigurable add-drop multiplexers. What we meant by reconfiguring meant that we could choose the wavelength. But when we bought them, they were either 50 gigahertz or 100 gigahertz ROADMs, and what we could change was the wavelength, and that among a couple of on the fixed grid for WDM. When we move to the elastic optical networks, now we need some sort of unit with a switching unit which has a tunable center frequency but also has a tunable bandwidth. And of course that tunability has got to be much finer with this new gridless system. It's still a grid, but a much finer grid. Fortunately, there are some technologies which have been evolving in order to meet these requirements. They're based either on liquid crystal on silicon or the microelectromechanical MEMS technology. So I won't talk about them, but I'll just say that in terms of technological readiness, there are devices available, have already been commercialized, and can be exploited for this requirement. So this gives you a sketch about what ideas we're trying to go to for the Flexgrid or the elastic optical network. So we can think of these as having three virtual wave bands, because if we look here in the frequency domain, for one particular destination we might use a waveband, but this waveband may or may not be contiguous. And each one of the contributing tributaries could have a different bandwidth or a different capacity. And so this is a real paradigm shift between what had been fixed grid on the previous optical networks. And I just want to remind you that there is trouble in paradise, that we had it easy in the fixed grid and the ROADMs. We could introduce enough guard band in order to protect the signal no matter how many switching units it went through. But here we have a little drawing that shows us how the bandwidth could change if we go through multiple hops. So we could tell the network all along that we're going to occupy this much, 150 gigahertz of the frequency and of the frequency band, and within that we'll have perhaps multiple segments. And as it propagates through the network, each time it goes through a unit which has to filter it to allow it through, we would get more and more of the corners of this thrown out. So you can't really design for an acceptable filter because it's gridless, so that means that this could be for one hop and the next hop might be different, so I'm going to have to be able to change this. We could use guard bands, but that would sort of defeat the purpose of what we're doing. So the important thing to notice is that quality will vary with the number of hops, and maybe this is something that we're going to have to deal with in our routing. And so this is an issue that we're still coming to terms with for the future elastic optical networks. So one of the key enablers was to have programmable modulations. So if I want to be able to have a reduction in the number of transceivers, I want to have a transceiver which could be bandwidth variable. That means that I could modulate at a programmable baud rate. Baud rate is also known as symbol rate, and it's the rate at which I am sending information. So it's not the bit rate. For instance, QPSK has 2 bits per second. So the baud rate would be half as fast as the bit rate, or since I'm sending 2 bits per symbol, it would be the bit rate is twice the baud rate. But anyway, baud rate is something I would like to be able to adjust. I would also like to be able to program the constellation size. And M is what I call the constellation size, the number of symbols in a constellation, because that allows me to adjust my spectral efficiency. So baud rate, so bit rate, as I mentioned, is the product of the baud rate, RS, excuse me, and the log 2, the number of bits per symbol. So I want to be able to adjust the bandwidth, and when I say adjust the bandwidth, that's really the baud rate, because the baud rate determines how much bandwidth I occupy. And how much information I actually get to transmit through the signal is this product. So higher M, higher baud rate. More bandwidth, higher baud rate, more bit rate. There is some trouble in paradise even when we have these programmable modulators, and that is that there is limitations in transmission distance, which is directly related to M. So the distance tolerance goes down as M goes up. So as I try to send more bits per symbol, if I go from BPSK where I send a single bit per symbol up to 16 QAM where I'm sending 4 bits per symbol, well, the distance that I can traverse to have the same quality of transmission is much greater in BPSK and gets much, much smaller. It's a nonlinear scale on the effect of system performance as M goes up. So routing challenges for the elastic optical networks are going to be much greater. So if we had something called routing and wavelength assignments in fixed grid, when we go to the Flexgrid, we're going to talk about routing and spectrum assignment. So it's not necessarily just a fixed wavelength, but it's going to be how should I divvy up my spectrum. And then I also enter into it, maybe I want to pick routing, modulation level, and spectrum assignment. So I get a lot more flexibility here, but I can imagine that the routing decisions are going to be much, much more difficult. So the elastic optical network essentially is based on assuming that switches and add drops are in place. In other words, that we are able to direct our wave bands, our flexible wave bands as necessary. Assume we have programmable transceivers in place, and then be able to route effectively. And when I want to say route effectively, what I'm saying is that we have to be aware of what the effective capacity of the system is, what the transparent reach of the system is, and the spectral efficiency. And I say the link, I mean for each one of the links. So in order to be able to do my routing, I can assume that these things are in place, but I have to have information or visibility into these qualities of the physical layer in order to do an effective routing at the network layer. So when I say effective capacity, what I'm trying to say is the bits per second, I have to remove any overhead incurred, for instance, in forward error correction or training sequence or pilot tones or headers or whatever. I have to know what that hit is so that I can come up with an effective capacity. In order to do an effective routing, I have to know what kind of distance is achievable for the quality of transmission required. And remember, I said there were different kinds of FEC thresholds I could use. So depending on whether I had a high overhead FEC or a low overhead FEC, I could achieve greater or less distance, for example. And also the modulation format I have will influence that. And finally, the spectral efficiency. And of course, that's by definition the ratio of the bit rate achieved divided by the bandwidth occupied. If I have zero overhead, then that would be m bits per second per hertz, where m is the number of, I'm sorry, it should be log 2m bits per second per hertz. So the problem, of course, is these three parameters, for instance, that I can adjust in my programmable transceiver. That's what I'm seeing here in each one of the rows, has a different impact on the qualities that I'm going to be using in my routing decisions. So my routing decisions, I'm going to base them on the effective capacity, the transparent reach, and the spectral efficiency. But when I'm in the transceiver and I'm trying to use my flexible transceiver to achieve these goals, I'm actually adjusting modulation format, baud rate, and FEC overhead, for instance. And they have competing trade-offs. So I would love to have everything, as I increase the modulation format, everything gets better, but of course that's not the case. And that's what makes this a very difficult problem. So as I increase the modulation format, my effective capacity goes up, more bits per symbol, but my reach goes down. I cannot go as far in distance because of that, but my spectral efficiency is going up. When I send information faster, baud rate, of course I'm sending it faster, so I'm getting more capacity. But I'm also reducing the reach because I'm letting more noise in because my bandwidth is larger. I can get a little bit better spectral efficiency because as I'm using wider bands, my guard intervals are going to be smaller. But also the FEC threshold. I can increase the redundancy in order to get better performance. For instance, I can make my reach greater, but that's going to reduce my effective capacity and also, by implication, the spectral efficiency. Just to show you that it's important to understand at the physical layer what we're able to achieve at the network layer. But there's also complex interactions and interdependencies that have to be taken into account in the routing decisions. So there's a lot of opportunities in going to more elasticity, more flexibility. We have finer control of our resources. It's no longer a coarse resource allocation, but very fine. So the finer granularity in the frequency domain in particular can be exploited, but this leads to more complex routing problems in order to achieve the capacity gains. And also, we have to justify the move to this programmable hardware is more expensive. So we have to be able to justify this move by having really achieving the gains that are possible. So you can see here the questions about how to do segmentation, aggregation, all these issues have to be resolved at the network level in order to take advantage of this move from a rigid allocation where everything is a single size, a couple discrete sizes, to much more granularity. And in this block diagram, we can see how these greater degrees of freedoms give you a lot of challenges in network management. So in the routing alone, we have to worry about physical impairments. In the spectrum allocation, we have to worry about whether we need to have contiguous carriers, what penalty we might be taking by separating the frequencies. Some modulation formats will work better with continuity. We need to determine what level of modulation, how many bits per symbol, what kind of symbol rate we want to assign, the FEC assignment. All of these are going to impact these decisions that we're making. Next, we'll be focusing again on the physical layer and going over some of the techniques that are used to enable the elastic optical networks. In particular, we'll be looking at two types of signaling, one known as Nyquist WDM and the other is the optical OFDM, or orthogonal frequency division multiplexing. And we'll look at the performance constraints on the optical network based on these physical layer characteristics. So let's begin with Nyquist WDM. The idea is to exploit the available frequency slot to the maximum extent possible. And in order to do that, we have to create a pulse in the time domain whose spectrum in the frequency domain stays as narrow as possible. Now, the problem of pulse shaping to achieve various goals has been solved by Nyquist, and of course this is the origin of the name of Nyquist WDM. And let's start with the basic idea that Nyquist said that we could have a set of pulses that we could be considered to be used, which avoids intersymbol interference by forcing 0 at the sampling points. And I'll try and give you some examples of what intersymbol interference is and how a Nyquist pulse avoids this impairment. And what's nice is that we can come up with a pulse that can be parameterized, allowing us to trade off exposure to this impairment known as intersymbol interference and the bandwidth occupancy. So for this application, we're looking at how is it that we can exploit the bandwidth as much as possible. But there are going to be some practical constraints we have to respect, and one of those constraints is based on intersymbol interference. Now, something called the ideal Nyquist pulse is a sinc function in the time domain, and I'll be showing you why we call it ideal. So let's start with rectangular pulses in the time domain. This is typically what we have in mind when we talk about digital data communications, that the information is sent during a given interval of time. So what we do at the receiver is, for a given interval of time, we'll do a sample, and that sample is at the center of this bit interval, and based on that sample's value, we'll determine whether it was a 0 bit or a 1 bit that was transmitted. Now, if we use a rectangular pulse, that means that when it comes time for the next bit, when we do our sample of what the next bit was, this particular bit will have been 0 at the time when we're sampling to get the next data bit. That means that there will be no intersymbol interference. That means this symbol in this time frame provides no interference to the next symbol. Because when the next symbol comes along and we're going to sample at the next symbol, this previous symbol will have gone to 0. And so there will be no intersymbol interference. But with this choice in the time domain, which has these great characteristics of a particular bit being isolated to a particular time slot, what we look in the frequency domain is that we have a sinc function. So that comes from Fourier transform theory. I start in the time domain with a rectangle, and in the frequency domain I have a sinc. But of course, in the frequency domain, I'm going to be allocating a particular frequency slot for this transmission. But the spectrum of the sinc function has infinite support in the frequency domain. That means that it is not isolated to the slot that was assigned to it. And of course, that means there could be crosstalk in adjacent channels because of this extension of the spectrum. So let's go to the other extreme. Suppose in the time domain I use a sinc pulse, and in the frequency domain I have then a rectangular pulse. So I have, in the time domain, what impact does this have on what I call intersymbol interference? Well, because I have a bit in the time domain which is not isolated to just the interval assigned to that bit, that means that these side lobes in the time domain are going to cause intersymbol interference. Of course, this intersymbol interference should not be too severe, because if we notice, the sinc function does have zeros at the time of the sampling for the next bit. Of course, there are a lot of imperfections in real systems, but at least because it should go through 0, this intersymbol interference should be small. And in the frequency domain, of course, we have this rectangular spectrum, so we no longer have crosstalk. So these are the two extremes. If we go with a rectangle in the time domain, or if we go with a rectangle in the frequency domain. Actually, we have a means of choosing between these extremes, or having a practical method of trading off different behavior. And this method is called the raised cosine pulse shape. And this raised cosine pulse shape is parameterized by something called the roll-off. And in this example, the roll-off is 1. And in a roll-off of 1, we have very low side lobes. So compared to the sinc function, we have much lower side lobes. But in the frequency domain, our occupancy is about twice what the narrowest possible occupancy could be. But what's interesting here is that we have a way of trading off, and in this trade-off, we're looking for very time domain isolated pulses, very small side lobes, so that the intersymbol interference would be almost negligible. But in the frequency domain, if we have to share our frequency domain with other users, of course, we risk having impairments coming from crosstalk rather than impairments coming from intersymbol interference. Now, if we go with a mid-range value of the roll-off, like 1/2, we can see we have some side lobes, but still not too bad. And they fall off, maybe the bit right next door to it might see some interference, but after that, maybe not much. And we can see now that we're using less of the excess bandwidth. In fact, the 0.5 means we have 50% excess bandwidth. In the previous example with 1, we used twice the bandwidth that we needed, so it was a 100% excess bandwidth. Here we're using 50% more than the minimum bandwidth for the ideal Nyquist pulse. And if we let the roll-off go all the way to 0, well, then we've gotten to the point where we have the sinc function of the time domain and 0 excess bandwidth, the narrowest possible spectrum. But of course, we can see here that compared to the other choices, the side lobes are much more pronounced. And so the chance that we would actually get some interference from adjacent symbols is much higher due to imperfections in timing, distortions introduced by different devices. So what's interesting about the raised cosine pulse shape is that it lets us choose the sweet spot, how much we're willing to trade off our frequency spectrum performance versus the intersymbol interference performance. And according to the DSP that we may be using, this may be relatively important or not important. So this is a graphic that shows you the range of possibilities for the raised cosine pulse shape. In the time domain, for instance, how isolated the main lobe is, how important the side lobes are. And in the frequency domain, the trade-off quantified in terms of excess bandwidth. And of course, it is, when we say it uses twice the bandwidth, of course, most of the energy is still concentrated in the desired band, but of course, this roll-off can change. And this way, we can quantify how much crosstalk will be generated by the use of that particular pulse, depending on how tightly packed the wavelength channels are. So this last one is the most spectrally efficient choice when we have a roll-off of 0. And this is when we talk about, in the optical domain, we talk about a Nyquist pulse. This is generally what people are talking about, the ideal Nyquist pulse. In order to generate this practically, we need a digital to analog converter. And at the receiver, we need some complex signal processing to continue the compensation for different impairments in the transmission. So this is the best exploitation of bandwidth. And the DAC, a digital analog converter, is a very versatile component to achieve this goal because it's very programmable. So we could easily use the DAC to slide, if we will, the compromise between ISI contributions and bandwidth contributions quite easily using this component. So in the optical elastic networks, what we would look at is something called a Nyquist WDM, maybe a super channel. So we would do, with a single DAC, we would achieve one of these channels, and we could use multiple DACs to line them up as tightly as we like in the frequency domain. And we would group them together and call them a super channel if we had, for instance, a large flow of data that we wanted to go from one point to the other. So the DAC bandwidth determines the width, maximal width that we can achieve in the single Nyquist WDM channel. But a super channel will group them together. So the idea with Nyquist WDM is to shape pulses in the time domain in order to achieve narrow spectrum in the frequency domain. And as I mentioned, it requires a digital to analog converter, and this has to have fairly good resolution. If I want to go from a roll-off factor of 0.5 down to 0.2, down to 0.02 to try and get as square a spectrum as possible, I'm going to have to use many bits per sample in order to get the coefficients for my filter, which will actually achieve that shape. We have to have a high sample rate because ultimately the bit rate that we can achieve is going to be determined by the sampling rate of the digital to analog converter. So it's how many bits per sample and how many samples per second I can get. On top of that, the DAC will have an RF bandwidth associated with it, and the performance is always better the wider the bandwidth that we can achieve for the digital to analog converter. But there are DSP techniques, which I mentioned earlier, which could be applied to try and compensate for the limited bandwidth of a DAC. So although we may have the two first ones improving, sometimes the third one lags, but we can try and compensate that. So the advantages of going to the Nyquist WDM is that we can have finer spectral allocations. I said we could go up to the maximum of the digital analog converter, but of course we can always use narrower bands also. And with this shaping, we get very sharp cutoff on those narrower bands. So going with the Nyquist WDM allows finer spectral allocations. And because we can make the cutoffs so sharp in Nyquist WDM, it also means that we should require fewer guard bands or smaller guard bands in our transmissions. The fact that we're shaping our pulses in order to achieve the goal in the network level, at the network level we're trying to pack more channels together, so that is a nice advantage, but we're also helping some of the components used in the system, because often the RF chain has components which are limited in bandwidth. And because we're forcing our pulses to be in the narrowest bandwidth possible, we actually are going to get less distortion from these other components. So there are some good factors that accrue, even at the physical layer, to this push for going for finer granularity and more flexible and elastic optical networks. So I've examined one of the possibilities for how we might achieve programmable and flexible allocations in the frequency domain. But there's another option on how we could achieve that goal, which is also very popular. And this is using optical orthogonal frequency division multiplexing. And I'm going to talk to you about how we generate these signals in optics. So last week we learned about orthogonal frequency division multiplexing in the context of 5G. And this technique in communications is also valid in optics. And especially, we see a big push towards OFDM, optical OFDM, being motivated by the possibility of supporting elastic optical networks. So there are two technologies that are used for generating these signals, and I'll be talking about both of them today. So the first option is to use electrical generation of the subcarriers. So this is really the same technique that we saw being used in 5G. However, in the optical domain, the bit rates are much, much higher than those that we see in the wireless domain. So although the ideas are similar, the devices required to achieve these are much more demanding in the optical domain than in the wireless. The second method to generate optical orthogonal frequency division multiplexing, OFDM, is to actually generate our subcarriers in the optical domain. This does not require an electronic FFT that we'll see is the basis for the electronic generation. Because it does not require electronics to generate the FFT, it can scale to wider bandwidths than the previous solution, and that is why we are looking at this second possibility. Although the optical generation of subcarriers is more a research topic and farther from commercial adoption than the OFDM. And there are a number of reasons for that, mostly because of the rich heritage that we have in OFDM from wireless and other applications. We have a lot of knowledge and know-how on how to exploit it, and a lot of the components have been developed, are already developed and applicable to that. So for this reason, the electrical is probably closer to commercial exploitation. So as I said, OFDM generation in the electrical domain is very similar to what we saw previously for the wireless. And just to remind you, we do a serial to parallel conversion of the symbols to be transmitted, and each one of these symbols is assigned to a frequency, a nominal frequency. The way we generate them is to go through an IFT, an inverse fast Fourier transform. So we interpret these symbols as being frequency domain symbols, and when we do the IFT, we convert them to the time domain. This digital signal is converted to analog, and in the previous case, we had antennas here. And the difference now is instead of an antenna, we have a DAC and an electrical to optical conversion. So I have an optical signal. The optical signal is sent over the fiber. Again, the time domain signal has a sort of irregular shape, but in the frequency domain, I would see the digital values assigned to each frequency. Now, after transmission through the fiber, we get to the other end and we do our optic to electronic conversion, and then we take the electrical signal that's analog converted to digital so that we can go into an FFT, and in the FFT convert back to the frequency domain where we can identify what were the data symbols transmitted on each one of the subcarriers. And so that's why I call this an electronic generation of the subcarriers, because there's actually only one laser being used for the electrical to optical conversion here. So there's one laser, but on this one laser we're going to see what looks like, if you will, virtual optical subchannels because of the FFT. So although I'm applying this analog signal to the single laser, when I look in the spectrum, what it looks like, I see the classic OFDM features on this laser. So I'll try to explain to you why OFDM is such a nice flexible solution in the physical layer. The first aspect was actually one of the reasons for adoption and development of OFDM first at this physical layer. And that was not for the reasons of the networking I mentioned, but about the sharpness of the roll-off of our signal. So, for instance, suppose I have 5 subcarriers. Each subcarrier is carrying 10 gigabits per second of data, just for round numbers, and say it occupies 10 gigahertz of frequency. Now, the total occupied frequency then is well, you can count it. We can see it visually. Suppose I double the number of subcarriers. Now, I double the number of subcarriers, but the total information being transmitted stays the same. So now each one of my subcarriers only carries 5 gigabits per second of data and only occupies half the bandwidth. So each one of the individual subcarrier channels is smaller and carrying less data, but the total amount of data is the same. And I can continue doing that, double it again, have 20 subcarriers, each one carrying slower data and occupying less frequency domain. Now, if I look at the overall spectrum of these solutions, I can see that at the edges of the channel, if we think of this as one super channel, if you will, or one OFDM channel, we can see the edges of this higher number of subcarriers has much sharper roll-off. And so we can see there's sort of the similarity between the OFDM solution and the Nyquist solution in that we're getting something that effectively is transmitting 50 gigabits of data, but instead of having a very rounded spectrum, which would come from, say, rectangular pulses in the time domain, without necessarily doing the Nyquist cosine shaping in order to achieve a rectangle, I'm getting something that looks pretty rectangular if I have a large number of subcarriers. So OFDM is kind of another way to compensate or to avoid the use of a rectangular pulse, which has a very wide bandwidth, another way of achieving very narrow bandwidth. So it's a completely different technique which comes around to achieving the same goals. And I want to mention another advantage of going to OFDM in terms of DSP complexity. And in that case, I'm looking at the equalization that I would have to do at the receiver end. Equalization is the digital signal processing used to overcome a variety of impairments that could arrive during the physical layer link. And these impairments could come from equipment, could come from the propagation, the transmitter receiver equipment, it varies. When I do an equalizer, the faster the transmission, the more complex the equalization, because my digital signal processing has to be running very fast. For instance, suppose I had one subcarrier, a single carrier system at 50 gigahertz. I would have to have my digital signal processing running at 50 gigahertz. With OFDM, I do my equalization on each one of the subcarriers. And in this case, the more subcarriers I have, the smaller or the slower the transmission on a per subcarrier basis. This means that in the extreme, I can get very good equalization even at easy parallelization and actually less complexity. So without going into too much more details, I'd just like to say that one of the advantages in going to a higher number of subcarriers, here I talk about the sharpness of the roll-off, but it is also, I would say, the ease or advantage in doing equalization via OFDM. I think I have another counterpart to that, or counterbalancing that effect. So I said that as I increase the number of subcarriers, I'm getting my equalizer to be easier. However, as I go to more numbers of carriers, subcarriers, my FFT size is getting larger. So in some ways, I'm increasing the complexity of my DSP because part of my DSP is just doing the fast Fourier transform. And of course, the bigger the fast Fourier transform, the more complex the DSP in terms of power consumption and size, physical size. So we can see that OFDM is a very nice, flexible solution because I can vary the number of subcarriers, the granularity of my solution. But it's not clear what's the sweet spot and which size we could do. My examples here, 5, 10, and 20, were just to be able to easily visualize them. However, in practice, typical sizes would be more like 256,024 this size of number of subcarriers. So again, one of the key components, or the key component in adopting optical orthogonal frequency division multiplexing, is the digital to analog converter. So again, this is a means of complete programmability. So it's very easy for me to vary the subcarrier number just by changing the programming going into my DAC. I can also vary the subcarrier spacing, and of course what I mean by that is the bandwidth being occupied. So just like we saw with the Nyquist filter, the Nyquist pulse, that we could use the DAC at the maximum of its bandwidth, or we could program it to exploit less bandwidth. We could do the same thing in the orthogonal frequency division multiplexing as well. We could also apply predistortion as a DSP technique that allows us to overcome some of the DAC limitations if necessary. So because this is so flexible and programmable, there are many tricks that we can use to apply to OFDM. Now when we use a DAC, of course, there are some limitations on the DAC. The bandwidth is limited overall by the DAC technology. And if we look historically, it's been very slow to improve the bandwidth, in particular, of the DAC. It's just hasn't, I would say it's a slower rate than Moore's Law, and we're going to see not big improvements in, well, what can I say? I can't predict the future, but just I think slower improvement in bandwidth of DACs than other components that we've seen. And they're also a source of more power consumption compared to traditional methods. So all this to say that DAC is a key component, but there are some challenges in this technology that really should be identified and improved as well. So far I've talked about the electrical means of generation of subcarriers, and now I'd like to talk about the optical generation of subcarriers. And in order to appreciate that, I just want to highlight again that the previous solutions, whether Nyquist WDM or the electronic version of generation of optical OFDM, in each case they used a single laser source for the frequency slot that was being used. Now I'm going to contrast that with the solution on the optical generation of subcarriers. So in this optical generation, there's no FFT, so this is not OFDM generated digitally. The subcarriers are laser lines which are locked together. So for instance, here's a collection of 4 subcarriers nominally on one wave band. However, instead of having a single laser at the center of the band, I will have 4 lasers, one for each of the subcarriers. So because I am applying my modulation to individual subcarriers, I have less granularity than I would in the electrical version, because each one of these is going to be much wider band. It makes sense that I get less granularity because the reason I go to this is to be able to increase the capacity. So I want to be able to send more information. So of course it's going to be a wider band, of course it's going to be less granularity, but my capacity, my ability to transmit data is going to be much higher. So what happens is each one of the laser lines is modulated separately. However, they are grouped and spaced so that they could look like an OFDM signal. And so we could have here 3 different OFDM channels, if you will, but each one of the OFDM channels in this case is generated by a different laser light source or a different laser line. So I mentioned that the DAC has limited bandwidth, but I could, for instance, this is one way of implementing, use it to create a Nyquist pulse. So I use a DAC, I use it on a single laser line, and I create something that is as wide as my electronics can achieve. Then I can sort of allow the overlap or the very tight spacing that I see in OFDM, and therefore get some economies in the spectral efficiency because I have used the OFDM idea, but I've used the Nyquist pulse idea to get the maximum I can out of my DAC. So the DAC is used to generate a Nyquist pulse, and the separate carriers are used to do the grouping into an OFDM superchannel. So let's see how we can compare these different options on achieving programmable, reconfigurable, very high capacity solutions at the optical physical layer. So let's start with the optical generation of OFDM. In this illustration, as I mentioned, we would have 4 subcarriers per OFDM signal, and here we have 3 of these optically generated OFDM grouped together in a super channel. And what we notice about this version is that it's very wideband. Because it's optically generated, there's no DAC. So this is a very wide band. We don't have the sharp roll-offs, and probably we will need more guard bands. Although the whole scale is larger, and therefore I can push through more data, it has also got the disadvantages of that reduced granularity, which is also going to apply not just to the data that I can transmit, but also to the way I can pack these super channels together. Now let's look at the electrically generated OFDM. In this illustration, we have 256 subcarriers, and we can see a very, very sharp roll-off. And the side lobes are very low and causing some crosstalk perhaps, but we can pretty much have very small guard bands. And that's true even at the super channel, where we've grouped several of the carriers together. So just to remind you, here we would have had used 4 lasers for this channel, whereas in this one we use a single laser, and all of the 256 subcarriers are sort of virtual subcarriers. They're generated in the electronics as part of the FFT. But when we look at the spectrum, we can see them clearly. And the third choice is, of course, to use Nyquist signaling. And this is, again, electrically generated. And it cannot be very wideband compared to the optically generated OFDM, because the width here, in the end, is determined by the DAC's maximum sampling rate, maximum speed. But very sharp roll-off is possible, and again, very little guard band is used. So in this respect, I would say that OFDM and Nyquist have really the same capability. It's just different ways that we exploit it, different techniques for generation, which DSP is used in each case. So comparing the 3, as I mentioned, the electronic solutions are giving the solutions with the tightest packing, the most spectrally efficient. However, the optical one has the potential of pushing capacity up higher. So they're still being investigated. The electronic version is something for which a lot of technology and know-how already exists, and will be closer to commercial deployment. OFDM is perhaps a better choice than the Nyquist for some of the same reasons we saw in the 5G application. Because I have a very high number of subcarriers within it, if I have to do a assignment of resources on a finer granularity, it's easy to do this in OFDM, much more than in Nyquist. So for this reason, we might prefer going to this multi-carrier solution, multi-carrier, there's many subcarriers, in OFDM rather than in Nyquist. So what we've seen are three approaches to the physical layer for the elastic optical networks. So we've seen optical subcarriers, where we could vary the subcarrier spacing depending on the goals we're trying to achieve. We've seen the OFDM generated by electronics, where the FFT is responsible for creating each one of these virtual subcarriers. And we've seen the Nyquist WDM. So all three achieve programmable, reconfigurable, but with different advantages. Now I want to just make the case for the section where I talked about how we were achieving the Shannon limit. I mentioned to you at that time all of the innovations in the optical physical layer in terms of modulation and advanced modulation formats. And we saw this receiver as being the technology that allowed us to achieve those goals with advanced modulation. We had here an IQ modulator, and we had here a coherent detector. Coherent detector which was able to detect both phase and amplitude. We needed the DAC at the transmitter in order to achieve the IQ modulation. So we can see that this hardware solution is exactly the same if I said, what do I need in order to have a Nyquist or OFDM generation for the flexibility in the elastic optical network. So all of this technology readiness that I described comes from trying to achieve other goals, just trying to push bit rate, but it also has brought us to the point of sophistication where we could use the same components to do double work, if you will. So we're going to combine this Nyquist, this pulse shaping, but also use the IQ modulation in order to do this in both in this two-dimensional constellation. So all of these three approaches, they all give us the flexibility that we requested, that I talked about in the second section, where we, the third section today, where we talked about how we would want to play with modulation format, play with symbol rate, and the spacing to achieve a more effective use of resources. In the previous section on elastic optical networks, I talked about how different parameters in our advanced modulation formats affected the three characteristics which were most important to exploitation of the resources, to make a more effective resource allocation. And that was the effective capacity, how many bits per second in the end could be put through, the transparent reach, how far could this signal at this rate go for a certain threshold on performance, on the quality of the signal, and what kind of spectral efficiency could be achieved, how tightly could I pack these channels. So those were the three characteristics that of course we wanted to be as good as possible, have this highest capacity, longest reach, best spectral efficiency. And we looked before at how changing modulation rate, the size of the constellation, changing the baud rate and changing the FEC overhead, how that had an impact. And now we can look at other characteristics that come from these methods of being as spectrally efficient as possible in a flexible way for these elastic optical networks. For instance, we could vary the number of subcarriers. By that I mean that we could add more subcarriers, create more, occupying more bandwidth. We could change subcarrier spacing, And we could change superchannel spacing, the spacing between the guard band in between. So let's look at each one of those and the impact that they have on the three characteristics used in the elastic optical network. So let's start with adding subcarriers. Well, essentially when I'm adding subcarriers, I'm going to add more carriers to this blue one, make it more wide bandwidth. So more subcarriers, what does that mean? That means I have more data that can be carried. So of course the effective capacity is going to go up because I'm carrying more information. But more subcarriers also means there's more sources of imperfections. So I didn't get into them, but of course there's not perfect isolation between these subcarriers. When I'm doing my equalization, it's because there is some interdependencies and imperfections in the hardware lead to inter-carrier interference. So because of that, when I'm adding to the more subcarriers, I'm also reducing the transparent reach. And finally, guard band should be pretty much unchanged because, if anything, I'm going to get an even sharper roll-off. So I'll assume that this guard band wouldn't have to change, or maybe might get better. So, so I would say that the spectral efficiency might go up a little bit because I have a little sharper roll-off. So let's go on to the next characteristic, which is the subcarrier spacing. So if I have the same number of subcarriers, that means the same amount of data is being carried, so I don't have any real change in the capacity. More separated subcarriers, well, that would allow me, in this case, for the optical generation of OFDM, to have fewer interactions between subcarriers. So I might be able to make my transmission distance go a little farther. But of course, if I put more spacing here, the same data is going to be occupying more bandwidth, which means the spectral efficiency is actually going to go down. And I could also play with superchannel spacing. That is, I can play with this guard band in between channels. Again, I'm only changing the guard band, so the data rate is not changing. More separated means I'll have less crosstalk from other channels, which means my signal will have better quality, and therefore my transmission distance could be longer. But the occupied band must increase because I have to have space for this guard band, so that means the spectral efficiency would go down. So that brings me to the end of my discussion of what the physical layer must do in order to accommodate the elastic optical networks. And we saw how these constraints would influence the parameters used for the network resource allocation. So I'd like to just now go to some brief concluding remarks. We started off by looking at the three waves of improvement that we saw on the physical layer of optical networks. We started off with a solution which used a single wavelength, and we saw improvements, steady improvements, mostly attributed to electronics, which became faster, and also improved fibers, so that the loss the dB loss per kilometer was also going down, which allowed us to go faster farther. Then we moved to the second wave, where we used extensive use of wavelength division multiplexing. And this was enabled by the Erbium doped fiber amplifier. And so we saw years where very fast growth in the capacity, bits per second, of transmission links by exploiting as much WDM as we could. More recently, we've seen the move into advanced modulation formats, which have shown us where we can approach the Shannon limit. So here, this dashed line is what's called the nonlinear Shannon limit. The theoretical Shannon limit I presented to you is overly optimistic for optical channel where for high powers a lot of nonlinearities occur. And I'll just say as a foreshadowing for next week's discussion, we can see that in this progression, we've seen how flattened the curve comes. And we're really worried about, as we go out into future years, are we able to maintain the growth in transmission capacity that we've seen in previous years. And I'll be talking about a new technology to try and move this curve up above this nonlinear limit, and I'll be talking about that next week. In terms of what we saw this week, we saw that this third wave, although it had flattened the increases were not as substantial as what we had seen in earlier. In fact, the move to advanced modulation formats has pushed us into a place where we can do more in the networking domain because we have the enabling technologies developed under this advanced modulation. So I talked about the technology readiness coming from these moves to advanced modulation. And the readiness was in what we call wavelength agile transceivers, that these transceivers are able to work on any assigned wavelength. And this has been enabled by two technologies, coherent detection, so the detection of advanced modulation formats also gives us the ability to easily tune to a particular wavelength by exploiting tunable lasers. So these two technologies have been key in developing transceivers which could be easily assigned to any wavelength, easily reconfigurable, both at the receiver and the transmitter. We've talked very briefly, I didn't say much, but there has been work in these programmable filters. So there was a lot of interest in the liquid crystal on silicon to create wavelength selective switches, which are currently used in the ROADM technology, which could also be redirected towards a Flexgrid solution. And MEMS devices have been developed for different switching applications, many filtering and switching applications, and now we can see that the sweet spot to use these in filtering is perhaps a time when this technology can come into its own in this new application. And in the last section, I talked a lot about digital to analog converters and how key they are in enabling Nyquist filtering or Nyquist pulse shaping, and also in OFDM. So this is a way for us to be able to sculpt our electronic signals in a way to achieve the best kind of spectral efficiency. So that has been on the physical layer, what is impacting what we want to achieve, and we can see that there's still lots to be done. There's a lot of research still going on under the devices, trying to get better DACs and ADCs. We can see that a lot hang on these devices, and so there's a lot of move to try to improve them. There's a lot of activity in integrating optical devices with the CMOS electrical devices. So we have a lot of DSP going on, either generating the OFDM at the start before it goes to the DAC or after the ADC, and processing our signal to get the best performance out of it. So we are now looking at integrating optical devices on the same manufacturing fabrication process for CMOS, which is what we're using in our electronics. So we're going to be able to see much lower costs in these components if we can get the integration to happen on the same transport. And so we're looking at this for modulators, and we're looking for this for coherent receivers. So that's a focus of a lot of research. And of course, switches and ROADMs have to be updated in order to have the capacity of not just having a programmable wavelength, but also be able to change the width of the spectrum that's sliced and the finer granularity on the positioning of that frequency. And although I only touched on it lightly, of course, there's a lot of research in the networking side to be able to create new routing algorithms and better resource allocation algorithms that takes advantage of this new adaptable physical layer. So, thank you for your attention.